Have you ever stopped to think about how scientists can predict, the exact path of a planet or figure out what happens in a car crash? Well, it's not magic, it's a language, and it's an incredibly precise language that describes motion. And today, we're going to learn the basics of that language by looking at something we've all done, just going for a simple drive.
So here it is, our car, heading out on what looks like a totally normal trip. It moves forward, it stops, maybe it even backs up a little. Seems simple, right? But to a physicist, this isn't just a drive. Oh no, it's a story, and it's absolutely packed with information about its journey. We're about to learn how to read that story, to see the physics hiding in plain sight. And that really brings us to the big question. I mean, you could say the car drove down the road a bit and then came back, and you wouldn't be wrong. But physics demands more than that. It wants numbers, it wants direction, it wants the specifics. So how do we describe this journey with the kind of precision a physicist needs?
Well, the tool we're going to use is called kinematics. I always like to think of it as the grammar for the language of motion. It gives us the rules to describe how things move without getting all tangled up in why they move. For now, we don't care about the engine or the friction from the tires, just the motion itself.
Okay, so first things first. Before we can even begin to talk about movement, we have to agree on how to talk about location. This all starts with the basic ideas of position and displacement, and we'll see how they're a little different from a word we use all the time, distance. Let's start with position. Sounds easy, it's just an object's location. But location relative to what? See, physics always needs a reference point, a starting line, what we call an origin. In this case, it's that 0-meter mark. So when the car is at point A, its position is plus 30 meters. But at point F, it's negative 53 meters. That little plus or minus sign is so important. It just tells us which side of our starting point we're on. Now, once an object actually moves, we can talk about its displacement. And this is a really critical idea. Displacement is not the total ground you covered. It's just the change in your position from your start point to your end point. And since it's just your final position minus your initial one, it can be positive or negative. Anytime you have a quantity in physics that has both a size or magnitude and a direction, we call that a vector. And this image makes it super clear. Imagine you walk along that squiggly blue path. The entire length of that path you walked, that's the distance. But your displacement, that's just the straight green arrow, the most direct line from where you started to where you ended. As you can see, they can be two totally different numbers that describe the exact same trip. So let's lock this down. Distance is what we call a scalar. It's just a number, no direction attached, like saying you walked 10 kilometers. Your car's odometer, for instance, tracks distance, and that number only ever goes up. But displacement, like we said, is a vector. It has to have both a size and a direction, like 5 kilometers east. It only cares about the net change from your starting point. And here's where it gets kind of mind-bending. Think about a basketball player running sprints. They run all the way up the court and all the way back, covering a huge distance. They're totally exhausted, but if they end up right back where they started, what's their displacement? It's zero. That's right, zero. They've moved a ton, but their net change in position is absolutely nothing. Okay, so we've got a handle on how to describe where something is and its change in position. But what happens when we ask how fast it's moving? Well, that's when we have to bring in the element of time. And that gets us to the heart of what most of us think of when we think about motion. And just like we saw with distance and displacement, there's a really common point of confusion between speed and velocity. Your car's speedometer, that shows your speed. It's a scalar, just a number. But velocity is a vector, which means it includes direction. Hearing that a storm is moving at 50 kilometers per hour isn't really enough information. But hearing a storm is moving 50 kilometers per hour towards you, now that's velocity. And that is information you can definitely act on. So let's check back in with our car. This graph right here basically tells its entire 50-second story. By plotting its position against time, we can see everything, where it was at any given moment, when it moved forward, when it reversed. It's all right here in this one simple-looking curve. So, how do we actually calculate the car's average velocity? It's a pretty simple formula. You just take its displacement, that's the delta x, and you divide it by the time interval it took, that's delta t. And notice, we're using displacement, not distance. And that means our average velocity can be positive or negative, which tells us the overall direction of its travel. And here is the really cool part. Remember learning about rise over run in math class to find the slope of a line? Well, look at this graph. The rise is the change in position. That's our displacement. and the run is the change in time. So the slope of the line is the average velocity. For our car, if we look between points A and B, we can just calculate the slope and boom, we find its average velocity was 2.2 meters per second for that first 10-second stretch. But of course, in the real world, we almost never travel at a perfectly constant velocity. We're speeding up to merge onto the highway, we're slowing down for a red light. So how do we describe that change in velocity? Well, that brings us to our final key concept for today. And that concept is acceleration. It's simply the rate of change of velocity. Now, this is so important. Acceleration is not just speeding up. In physics, if you're slowing down, that's a change in velocity, so you are accelerating. If you take a turn, even at a constant speed, your direction is changing, which means your velocity is changing. So yep, even then, you are accelerating. A fantastic way to actually visualize this exponentiation is to imagine taking a snapshot of our car at the exact same time interval, say every 1 second, over and over again. The spacing between those snapshots tells us everything we need to know about its acceleration. Take a look at this top example. The car is covering the exact same amount of distance in each 1 second snapshot, so the images are all perfectly spaced out. That tells us its velocity isn't changing, it's constant. And if the velocity isn't changing, then what's the acceleration? You got it, it's 0. Simple as that. Now, look at the middle one. The spacing is getting wider and wider. The car is traveling farther in each time interval. That means its velocity is increasing, it's speeding up. This is exactly what you feel when you press the gas pedal. The acceleration is in the same direction that the car is moving. And finally, at the bottom, the spacing gets smaller and smaller. The car is covering less and less distance in each interval. It's slowing down, just like when you hit the brakes. In this case, the velocity is still pointing forward, but the acceleration is pulling backward, in the opposite direction. And that's what we call negative acceleration. So now that we have these incredibly powerful rules for describing position, velocity, and acceleration, we can actually apply them to one of the most common, most constant forces in our entire universe. And this brings us to the idea of free fall. In physics, an object is in free fall if it's moving only under the influence of gravity. It really doesn't matter if it was dropped from a standstill, thrown downwards, or even thrown upwards. The second it leaves your hand, and if we ignore air resistance for just a moment, gravity is the only thing in charge. And here on Earth, that acceleration due to gravity is remarkably constant. Its value is about minus 9.8 meters per second squared. That negative sign is just a convention, by the way. It just tells us that the acceleration is always pointing downwards toward the center of the Earth. This single number governs the motion of everything from a dropped penny to a leaping frog, which leaves us with one final fascinating puzzle to chew on. If every single object in free fall experiences the exact same acceleration, no matter how heavy it is, then why doesn't a feather fall as fast as a bowling ball? What other force are we ignoring here? That is a fantastic question to think about, and it's a little peek into where physics goes next. Thanks for coming along for the ride today.